Welcome to the video help with physics problems for Physics 1A. In this video we'll be doing homework set 1 part 4, which is the second half of the questions under the heading Motion in 2 and 3 dimensions. For 1121 this will cover questions 11 to the end, and for 1131 this will cover questions 13 up to the end. So problem 11 for 1121 or 13 for 1131. In this one we have an automobile rounding a curve with radius 40 meters. And we're asked what is the speed such that the radial acceleration is equal to g. So the radial acceleration is given by v squared on r. So we have v squared is equal to ar times r, which is g times 40, and so v is equal to the square root of 9.8 times 40, which is equal to 19.79 or 20 meters per second. Two significant figures is 40 meters is to two significant figures. That's part A. Part B says, suppose that the automobile is travelling at this speed along a straight roadway but over a hill having a radius of curvature of 40 meters. So here it is going over the hill. This is 40 meters. What is the behaviour of unattached objects within the car? Well, when the car's here, we've got gravity acting down on it, but we also have the radial acceleration. AR is equal to G and FR is equal to mg. So these will cancel out. So at the top of the hill, objects in the car will appear weightless, as there's no force acting on them in the vertical direction. Problem 12 for 1121 or 14 for 1131. In this question we're asked to write down the equation using polar coordinates in I and j for a particle undergoing uniform circular motion. So here's our particle. It's going around and around a circle. This is the x-axis or the y-axis, and this is the y or the j-axis. Let's choose a point here. Now at this point it makes an angle of theta with the y-axis. It's a distance r from the centre, where r is the radius, and in the x direction it's got a distance r cos theta, and in the y direction or the j direction r sine theta. So to write down the position vector for this, we can write r is equal to r cos theta in the I direction plus r sine theta in the j direction. That's the answer to part A. In part B, it says use part A to derive the vector expression for the velocity. Okay, so the velocity is given by dr dt. So all we need to do is take the derivative of this. Now r is constant, the radius isn't changing because this is uniform circular motion, so with time theta is changing, not r. Okay, so let's pull r out as a common factor. So we've got r, and then we've got to do d dt of cos theta in the I direction plus sine theta in the j direction. So we can write r d cos theta d theta dt in the I direction, should be brackets, plus d sine theta d theta dt in the j direction. Now d theta dt is just omega, the angular velocity. So that appears in both these terms, so we can write that as omega and pull it out the front. So we've got r omega, d cos theta d theta is equal to minus sine theta in the I direction, and then d sine theta d theta, that's plus cos theta in the j direction. So that's an expression for the velocity. For the acceleration, we have to take the derivative of this. Now this is uniform circular motion, so omega, the angular velocity, is not changing. So this just stays as a constant out the front. So we have r omega, and then this time when we take the derivative, we've got d sine theta, d theta, d theta, dt in the I direction, plus d cos theta, d theta, d theta, dt in the j direction. Okay, so once again we can pull omega out the front. So we've got r omega squared. Now d sine theta, d theta, this is minus cos theta in the I direction, and this becomes minus sine theta in the j direction. So comparing this and this, we can actually write that this is equal to minus omega squared r. Okay, part C. Prove that the acceleration is directed towards the center of the circular path. Okay, well the radial vector is always directed outwards from the circular path. The acceleration is always negative, the radial displacement. And so if the radial displacement is always outwards, then the acceleration is always inwards. So C, this is because it always has the opposite direction to R. Okay, problem 15 for 1131. We're told that the particle moves in a plane such that x is equal to r sine omega t plus omega rt, and y is equal to r cos omega t plus r, where omega and r are constants. This is called a cycloid and is the path traced out by the point on the rim of a wheel, which rolls without slipping along the x-axis. For part A, we're asked to sketch this path. So here's x, here's y. The best thing to do is to substitute in different values of t and find out where our point is. So let's start with t equals 0. Sine of 0 is 0, so the x component is 0. Cos of 0 is 1, so the y component is 2r. So we start up here at 2r. Now let's try t is equal to pi on 2 omega. So at this time we've got sine of pi on 2. Sine of pi on 2 is 1, so this will be r, and this will be omega will equal r plus omega r pi over 2 omega. So this will be r outside of 1 plus pi on 2. And y at this point, cos will be 0, so y will equal r. So that'll be, here we'll have r, and here we'll have r outside of 1 plus pi on 2. And now let's look at when this is 0. Y is equal to 0 when omega t is equal to pi. So that tells us that t is equal to pi on omega. So when t is equal to pi on omega, y is equal to 0, and x is equal to, this is 0, so we've got omega r, and then t is pi on omega. So this is equal to r pi. So we've got r pi here. Now we continue this process substituting in different t's, and we find that we get a cycloid curve like this, where this is 3 pi r, this is 5 pi r, etc. Part B, we need to find the instantaneous velocity and acceleration at a few points. So probably the best way to do this is to find the generalized formula for these, and then we can substitute in the specific points we're interested in. So the velocity in the x direction is equal to dx dt. R and omega are constant. So we've got r d sine omega t dt plus omega r. Taking the derivative of this, we get r omega cos omega t plus omega r. The acceleration in the x direction, we take the derivative of this, so this is dvx dt, which is equal to r omega squared sine omega t with a negative, and this is constant, so when you take its derivative it disappears. In the y direction, we've got Vy is equal to the derivative of this, which is minus r omega sine omega t. When we take the derivative of r, it disappears, and Ay is equal to the derivative of this, which is minus r omega squared cos omega t. Okay, now we're asked to find this at particular points and its maximum and minimum values of y. Okay, so we can substitute in t equals 0 for the maximum. So for the maximum, we've got Vx is equal to, well, cos of 0 is 1, so this is 2 omega r. Vy, substituting in t is 0, this goes to 0, and we have Vy equals 0. Ax is equal to, substituting in 0, we have 0, and here substituting in 0, we have Ay is equal to minus r omega squared. Now, t is equal to, we said pi on omega at the minimum. So substituting that in, Vx, we've got cos of pi. Cos of pi is minus 1, so this is actually 0. V of y, we've got sine of pi. Sine of pi is 0, so this is 0. A of x, sine of pi is 0, so once again a of x is 0. And substituting in, we've got cos of pi. Cos of pi is minus 1, so a of y is equal to plus r omega squared. And that's the answer to this problem. Okay, we're now up to problem 16 for 1131. Okay, in this problem we have a ball which is projected upwards with velocity v0. It starts at height h above the ground, and it's projected at an angle theta naught. So initially we can divide its initial velocity into a horizontal and a vertical component. The horizontal component is given by v0 cos theta, and the vertical component by v0 sine theta. Part A, we're asked to write down equations giving the horizontal and vertical coordinates of the shot at time t. So the horizontal components are given by x is equal to, now in the x direction it just moves with the constant velocity, so this is just v0 cos theta t. Now in the y direction it starts at height h above the ground, so we've got h plus the initial y velocity v0 sine theta t plus the acceleration due to gravity, which is actually acting downwards, and so that's a negative, so it's minus a half gt squared. Okay, in part B we're asked to eliminate t to find the range. So part B, we can rewrite this as t is equal to x over v0 cos theta. And then we substitute this into this equation. So the range, well, we have the distance travelled is equal to h plus v0 sine theta x over v0 cos theta minus a half g times x over v0 cos theta squared. So rearranging this, we've got h plus v naught x over v naught. These v naughts will cancel, and sine theta on cos theta is tan theta, minus a half g x squared over v naught squared cos squared theta. So we can write that as sec squared theta. And now it'll hit the ground over here when y is equal to minus h, when y is equal to 0, and x is equal to the range. So what we want to do is substitute in y is equal to 0 and rearrange this to find x. So let's let the range equal capital R. Okay, so we've got 0 is equal to h plus r tan theta minus gr squared over 2v naught squared sec squared theta. And that is actually the equation that we were asked to derive. Okay, now we need to take the derivative of this with respect to theta. The derivative of tan theta with respect to theta is sec squared theta, and the derivative of sec squared theta is sec squared theta tan theta. When we take the derivative of h with respect to theta, h is independent of theta, so that goes to 0. So what we'll need to use is the product rule. We've got dr d theta tan theta plus r d tan theta d theta. And then we do the same for this term. G2 on v naught squared are all constants, so let's get rid of that plus, it's a minus. So we've got minus g over 2 v naught squared dr squared d theta sec squared theta plus r squared d sec squared theta. It tells us in the question to set dr d theta equals 0. So this is 0, and dr squared d theta is equal to 2r dr d theta. So this is also goes to 0. So we've got r, the derivative of tan theta is sec squared theta, minus g over 2v naught squared, we ignore this term at 0, r squared, the derivative of sec squared theta is sec squared theta, tan theta. It's a standard integral. Okay, now we've got to try and solve this for maximum range r. So we have g over 2v naught squared r squared sec squared theta tan theta is equal to r sec squared theta. We cancel out the sec squared thetas and one of the r's, and we have r is equal to 2v naught squared over g tan theta. Okay, now we lost a factor of 2. The derivative of d sec squared theta d theta is actually equal to 2 sec squared theta tan theta. So that's where that 2 went. Okay, part D. By substituting r in b, so b we had 0 is equal to h plus r tan theta minus g over 2v naught squared r squared sec squared theta. We need to find theta m. So we're given that rm is equal to v naught squared over g tan theta m. Okay, and we're told to substitute for r. So 0 is equal to h plus v naught squared over g tan theta m times tan theta, and then this will be theta m for the maximum range, minus g over 2v naught squared. Now we substitute for r, so we've got v naught to the 4, because this is squared, g squared tan squared theta m, sec squared theta. Let's write sec squared theta as 1 on cos squared theta m. Okay, so this is h plus, now these cancel, so we've got v naught squared over g minus, this cancels with 2 of those, this cancels 1 of those, so we've got a half v naught squared over g. Now tan squared theta, we can write this because it's 1 over tan squared theta is equal to cos squared theta over sine squared theta. So this and this will actually cancel out, and we'll have sine 1 over sine squared theta m Okay, now we need to rearrange it to get this by itself. So let's write a half v naught squared g 1 over sine squared theta m is equal to h plus v naught squared on g, which is equal to hg plus v naught squared on g, just in case that helps. We can write 2g sine squared theta m over v naught squared is equal to g over hg plus v naught squared, and then sine squared theta m is equal to v naught squared g over 2g hg plus v naught squared. These g's cancel out and we end up with v naught squared on 1 over hg plus v naught squared, which is almost what we were asked to show. To get what we need to show, we just need to divide the top and the bottom by v naught squared. So this is equal to 1 over 2 hg over v naught squared plus 1, which is what we were asked to show. Now part E, champion shot putter is able to impart initial speed, so v naught is equal to 14.0 meters per second on the shaft. Calculate the optimum angle and distance of the throw. Take the height equals 2.1 meters. Okay, so first of all we should calculate the optimum angle. We can use our answer from D. Sine squared theta m is equal to 1 over 2, 1 over 1 plus g h over v naught squared, which is a half 1 over 1 plus 9.8 times 2.1 over 14 squared, which on the calculator gives us sine squared theta m is equal to 0.45, so theta m is equal to 42.3 degrees. And then the maximum distance Rm is equal to v naught squared over g tan theta m, so that's 14 squared over 9.8 times tan of 42.3, which gives us 22.0 meters. Part F, explain without any mathematics why the angle for maximum range will be slightly less than 45 degrees. Okay, if the projectile was going from the ground, then the maximum range would be at 45 degrees. However, this projectile is being projected from an initial height, so it's going like this. So letting it go from this height effectively gives us a little bit of extra time to travel before it hits the ground again. This would be like, it's got this bit of extra travel here. So in this case, it's useful for it to have a little bit of an extra horizontal velocity so that it can travel a greater distance with that extra time. So the angle will need to be a little bit less than 45 degrees to give it just a little bit more horizontal velocity. Past exam question. Okay, so a bird is flying overhead with a speed v bird is equal to 5.0 meters per second in a straight horizontal line, and it's 5 meters above your head. So here's 5 meters, here's your head, and you're going to throw up some grape. And it occurs to you that the bird might want one, but you don't want to hurt the bird, so you want to throw it up so that at some time t, it has the same velocity and height as the bird, so that the bird can have the grape like that. You throw it up at some angle theta to the horizontal. This is theta here. Part 1 asks, should the bird be behind you or ahead of you when you throw the grape, and by how much? Explain your answer briefly. Okay, well, when the bird gets the grape, you want the bird and the grape to have the same velocity. So the grape has to have a velocity of 5.0 meters per second here. The horizontal velocity isn't changing if we neglect the air resistance. So that means that you need to throw it up with a horizontal velocity of 5 meters per second, which means that as soon as you let go, it has a horizontal velocity of 5 meters per second, which the bird also has. And so since the grape and the bird have the same horizontal velocity, it's not possible for one to overtake the other. They'll always travel together. So you need to throw it when the bird is directly overhead. As the grape and bird. The same horizontal velocity and so cannot overtake each other. Part 2. We need to calculate the required values of V0 and theta. Okay, let's expand this diagram a little bit. Here's theta. Here's V0. And this, we said the horizontal velocity was always the same as the bird's. So this is 5.0 meters per second. Okay, so V0 cos theta is equal to 5.0. That's one point. The other point is that when it reaches the bird, so when it's gone a distance of 5 meters per second, the vertical velocity must be 0. So, okay, now this is the initial vertical velocity, and we know that when the grape is 5 meters above your head, it has 0 vertical velocity. So at 5 meters, Vy is equal to 0. So we can use the equation Vy squared is equal to Vy0 squared plus 2ay. We know the acceleration is due to gravity, so it's 9.8. So 0, this is up here at 5 meters above your head, is equal to Vy0 squared minus 2 times 9.8. These have the opposite direction. Initially it's going up and the acceleration's down, times y, which is the 5 meters. So we have Vy0 is equal to, on the calculator we get 9.9 meters per second. Okay, so this one here is 9.9 meters per second, and this one's 5. So V0, we can use Pythagoras to solve. 9.9 squared plus 5 squared, which gives us 11.1, which is just 11 meters per second. And then substituting in here, we've got cos theta is equal to 5 over 11. So theta is equal to 63 degrees. Okay, part 3. If the air resistance on the grape was not negligible, how would that change your answer to 1? Okay, so if the air resistance was not negligible, then the grape would be slowing down as it covered the distance, which means that you would have to actually throw it with a greater horizontal velocity to start with. So initially it would have a greater horizontal velocity than the bird, and so it would cover that distance faster because over most of the distance it has a greater velocity, and so you'd actually have to wait until the bird had passed overhead to throw it. You wouldn't throw it at the instant the bird was overhead. You'd wait a little bit and then throw it.